one sample mean. You can use it for the melatonin example if you like. It's maybe 2 another sample mean is equal to, we're gonna make it a little bit different, equal to say 11, and another sample mean is equal to 12. Okay. Let's say that's how your data came out to be, or melatonin example, or whatever example you like. If you look at that data, right, those means representing data, and you had to do one comparison on that data. You have to do one comparison on that data. And it could combine groups as well. It doesn't have to be just one mean versus another mean. It could be 2 means versus another mean. Okay. What comparison would you do? 1 to 2. 2 and 3. 1 to 2 and 3. Okay. Now, you've made this comparison. Would anybody make a different comparison? No, right? You'd make this comparison. If you had to make one, why? Because that's the one that's probably going to come out to be what? Statistically significant, right? If you had to make one comparison, you'd probably do this, because this is probably going to give you the biggest shot of getting, say, p is less than 0.05. It's the comparison that you think is going to come out. Okay? That's an entirely different situation that what we just did than if I asked you, what comparison would you like to make? This is before you've obtained the data, or at minimum, before you've looked at it, right? Before you've obtained it, or before you've looked at it. It could have been in a vault for 10,000 years, and you haven't seen it. Now, what comparison would you make? You know nothing about the numbers, you know nothing about the actual observations. What comparison would you like to make? Again, the same similar idea as what we did before, but give me the comparison. Well, if you say, well, the comparison I'd like to make on this data is between this mean and this mean, even though it's the comparison of the same means we just did prior to that, what's the difference between these two scenarios? What's the difference between these two scenarios? One of the scenarios gave rise to post hoc tests. The other one is just comparison. It's just contrast and comparisons. What's the big idea here? Again, understand this distinction. Post hocs will never be a mystery for you. You'll always understand it. And we'll look at a few sample ones. What's the big deal? Which is the more impressive comparison in line with me dropping the marker and stuff like that? Which is the more scientifically impressive, or stands to be more scientifically impressive? Contrast. Yeah, probably the contrast, right? In other words, making this comparison before you look at the data, say, you know what? I think mean 2 and 3 are going to be different from mean 1. What does that require? That requires some predictive ability, based on past research, even based on a hunch, but based on something where you're going, according to my studies, this should happen. According to my scientific investigation, the big earthquake in California is going to be happening in 5 years. That's entirely different than the next morning going, the big earthquake happened. When you look at the data, and it's 2, 11, and 12, that's like saying the earthquake happened yesterday, I told you so. That's not impressive, because when you actually made this comparison of 2 versus an 11, 12, did you really just make that comparison? So I can go back to this and say, which comparison would you make? You say 2 versus 11 and 12. And I say, is that the only comparison you're making? What do you say? Is that the only one you're making there? Yeah? Okay. How many people buy it? How many people say, yeah, it's the only comparison I'm making. Look, 2 versus 11 versus 12. Okay, so you look at this, you say 2 versus 11 versus 12. How many comparisons have you made? Just one, right? No, I don't believe you. Nor does the post hoc test. How many comparisons are you making? A lot more than that. You made a lot more comparisons than that, and then you said, well, why don't I end with the earthquake happened. Why don't I end with making this one, because I think that'll make me more successful in getting this and finding a difference, right? But when you look at the data, you're making a lot more comparisons than what you're actually testing. So when you looked at it, what did you do? You went, well, 2 is pretty different than 11. 11 isn't very different from 12. You looked at that and then you concluded that that's the comparison you're going to make. So what's the rationale for post hoc tests? What's the post hoc? Everyone's heard of post hoc tests before. What's the rationale for the post hoc test? I mean, let's understand it from first principles as to why post hocs even exist. Do a Tukey, do a Chaffee, do a Newman coils. What's the purpose? I mean, we're doing fine. Why don't we just do contrast like this and just do mean comparisons, almost like a t-test, right? Almost like a t-test, compare this to this, this to this, this to this, and let's just find out where the differences are. So I'm gonna suggest we just do this to this, this to this, this to this. Let's do some comparisons and find out where the differences are. What possibly could this invention contribute? The nature of the post hoc idea is in this example. What's the job of the post hoc? They bring in the post hoc person, they come in, say, explain to us how you're going to deal with this. Ideas. Why not just do a whole bunch of t-tests? Why not just do t-tests between mean 1 and mean 2, mean 2 and mean 3? Just keep doing t-tests and then maybe even combine them after. Just fully exploit the data, right? It's like surveying the wreckage the day after the earthquake. And saying, I think an earthquake happened here. Right? And I think the damage was worse in this side of LA than this side of LA, right? I'm pretty sure, and then you adjust your tie, because I'm a scientist. This is what I see, right? It really affected this side, and you go, wow, that's impressive. Could you have told us that yesterday? So what's the job of, I mean, we do the post hoc. When the scientists do that, they say the meteorite struck yesterday, and it's worse in Russia than it is in America, because that happened over there. Or when the winter storm happens, right? In end of September. It's like, it was worse in Cut Bank than it was for here. When the weather person says that the next day, what's your post hoc mentality?
Duh.
Yeah, you say duh. Why do you say duh, right? Why do you say duh? When they say it's worse than Cut Bank, which had it like brutal, compared to here, when they say that the next day, anyone could have observed that, right? And what do you say, well, that's not impressive. Why? You looked at all the data. You looked at all the data. You went to Cut Bank. You went, wow, pretty bad. Great Falls, pretty bad. Missoula, not too bad, not too bad. And then you just concluded that it was worse in Cut Bank than Missoula. You looked at the data. That's not impressive. Anybody could do that. So what's the job of the post hoc? What did you do up here that diminished the weather person's? I mean, why wasn't that impressive when they said that? Why would it have been much more impressive if the day before they said Cut Bank's gonna get it really bad and Missoula not too bad? And then the result happens, and then you say, my goodness, they actually do know what they're talking about. Why is that more impressive in terms of this example? So if you can predict where the difference is gonna be and make that comparison based on meteorological evidence, expertise in the area, things like that, forecasting models, that's like you haven't looked at the data yet. So when they say it's gonna be worse in Cut Bank than Missoula, how many comparisons are they actually making when they make that prediction, that particular prediction? One. Because they haven't looked at the result yet. When after they've looked at the result and they say, well, Great Falls, Cut Bank, they've looked at the data, so it's the duh principle, right? It's like, well, yeah, anybody could say that. What we really want is for you to tell us when the meteorite is gonna strike, not after it strikes. When you look at the data and you say, I'm gonna make this comparison versus this, anybody can do that. Anybody can do that. So what's the post hoc test gonna do? Well, you ran a mental post hoc when the weather person said it was worse in Cut Bank than Missoula, and you said, how much data have you actually looked at? let's correct things for how much data you've actually looked at. So when you make this comparison comes with an error rate, the type 1 error rate. What's the type 1 error rate you set at? Maybe it's 0.05. But you made that comparison. You made probably this comparison. You probably made this comparison. You made a whole bunch of comparisons. Nobody knows how many you made, but no one's buying it that you just made that comparison there. So in other words, with every comparison that you make, you're experiencing the risk of a type 1 error. So 0.05 plus 0.05 plus 0.05, etc. That error rate is going to compound and get higher, and it's not going to quite be a multiplicative effect like that. It's not like 0.05 times 3 comparisons, but nearly so. It ends up being a little bit different, but it ends up being, like in this case, maybe around 0.5 or something like that. That your actual type 1 error rate is closer to 0.05 than it is, closer to 0.15 than it is at 0.05. And again, that's because we assume you're making more comparisons. Now, nobody knows how many comparisons you have made. Nobody knows, but we assume you're making more comparisons than the particular data comparison that you're actually executing. Contrast that to if you don't have the numbers, then what's your type 1 error rate?
0.
Well, it's not 0. It's not 0. So when you make this comparison here, when you say, I'm going to compare this to this, you can do that at whatever you set your type 1 error rate at, like 0.05 or 0.01, and we have some assurance that that's the actual type 1 error rate that you're operating under. Yeah.
Is it because it's, I mean, I guess it's this, it wouldn't be random. A contrast isn't necessarily random, is it?
Well, it's not random. Yeah, that's a good question. It's not random, right? What's informing the contrast here? This is the exact reason why the contrast is permissible if you don't look at the data. Because if I go to this one, if I say mean 1 versus mean 2 is going to be different than mean 3, this is before the storm. This comparison that I'm making should be based on what? I mean, why am I drafting that comparison? I mean, what's it probably based on? So when I say, I think it's gonna storm in Cutbank, and it's gonna be worse than Missoula, what's that based on? Yeah, our knowledge, right? Our predictability, knowledge of the scientists. A meteorite's gonna strike in 2030, and it does. Wow, that's pretty good. Much different than if you look at the data. So the idea is, after you look at the data, nobody believes that your type 1 error rate is actually at the level you set the test at. You're gonna have to adjust for it. You're gonna have to adjust for it. You're gonna have to adjust for it because it's what? It's not at 0.05, it's probably much higher. What's the problem with the inflation of the type 1 error rate? So as it gets higher and higher, maybe 0.15, more comparisons, 0.20, whatever, as it gets higher, what's the issue with that? So who cares if you have an overall error rate of 0.20? I mean, what's the problem with this? 0.15, 0.20, 0.25? What's the problem from an experimental point of view, right? Remember, you look at research reports and you say, the type 1 error rate is 0.25. What does that mean? A quarter, 25% of this is just crap. That's the type of thing, right? Like, think of it, the street talk version of saying, maybe that's just due to chance. Maybe it's just due to chance. So you want to minimize the type 1 error rate. You definitely don't want to start letting it get too high. In some cases, you can let it get a bit high, but you definitely don't want to start looking at data and just making the comparisons that you think are going to turn out, and then fool people or try to convince people that that's the only comparison you're making. How about with 2 means? Let's just get rid of this. Just the 2. Let's just work through that scenario. What happens with the 2 means? Well, what's the problem with that? Cutbank versus Missoula. In that case, does it really matter whether I've made it before or after? No. Maybe the direction matters. Like if I said Missoula is going to get more snow than Cutbank, but the actual difference doesn't matter. Why? Because how many type 1 errors could you have made here? 1. There's 0.05. There's nothing to correct. There's nothing to correct. But as you add more means to the situation, you have to correct for the number of comparisons you're making. So what's one way of correcting for the number of comparisons? Well, one kind of easy way of looking at it is to say, you know what, if you're gonna make, say, 3 comparisons, so if my comparisons are equal to 3, then why not take my overall alpha, which we're gonna call the family-wise alpha, the alpha that's accumulating over the family of comparisons, and divide that by what? Let's divide that by C, the number of comparisons. So if my overall alpha I want to keep at 0.05, and I divide by 3, that's like 0.016 or something like that. It comes up to be about something like that. Right. Ideas of that. Is that a nice idea? Take your overall alpha rate that you want to have for the family of comparisons, the overall number of comparisons you're making, so you set that in advance. Say, you know what, overall comparisons, I don't want to make any more than this overall for my type 1 error rate. Just divide it by the number of comparisons you're gonna make. Divide by, say, 3, if you're gonna make 3 comparisons. And then test each comparison at the new error rate. Does anyone know what the correction this is called? No. That name, that correction has a very specific name. Starts with B. Bonferroni, and I keep forgetting how Bonferroni likes to spell it. Might be 2 R's, might be 2 N's. That's pretty close. Definitely not beefaroni like the undergraduates say, but Bonferroni. Okay, so Bonferroni. And this here, right? Okay, this is, what's this? It's not the fishy. Not the fishy. Looks like a fish. Okay, that's the undergraduates say the fishy thing. Is the fishy thing going to be on the test? That's alpha. If you want to have some fun TH stats. So 0.016. You're now a member of the higher club. You can now laugh at undergraduates. 0.016 is your new error rate per comparison. Now, what do we think of this? By splitting up the overall error rate by the number of comparisons. Is it a good idea? Bad idea? Test each of your comparisons at 0.016. Ideas? Good idea? At about 0.016. We know, I mean, what's the, maybe it keeps our overall family-wise error rate at 0.05, but what's the drawback of that?
Giving each variable like equal weight when there could be one that's.
Well, yeah, equal weight. I mean, we're making the comparisons. We're trying to make the pairwise comparisons here. And I mean, what do we think of this? As if I told you compare 2 means and use this as your criteria, so your alpha is you got to pass this.
You have a significant
It's gonna be
difference.
really
Yeah, maybe it's going to be harder, right? What have you lost?
Power.
Yes, absolutely. Excellent, right? You've lost power. See how the other comes in and say, hey, you want to do a Bonferroni correction? That's going to cost you a bit of power. 3 means not too bad if it's pairwise comparisons you want to make. What happens as the number of means gets larger? My goodness, right? Like I'm gonna like make 10 comparisons, and like it's gonna get ridiculously small. So therefore, if you have a lot of means that you're comparing, then I mean, at some point, it's like you just don't have enough power to do it. So this Bonferroni comparison, or the correction rather, the Bonferroni correction, because it's correcting the alpha level, the Bonferroni correction, it's usually suitable for like 3 or 4 means or something like that. Not too many more. Okay? Bonferroni can be used as a contrast. It can be used as a post hoc. Both options are usually acceptable, and you'll see them used in each case. So what do we mean by the contrast? Well, the contrast, and we'll formally define that in notes in a second, but the contrast is just the comparisons we're making before looking at the data. So you're doing a contrast before looking at the data. If you're doing it post hoc, then what's the idea of post hoc? Well, it's after looking at the data. Well, doing this after looking at the data, it's still a fair way of getting a handle on that type 1 error rate. Right? It still tries to control it, even if you look at the means. Even if you look at the means. So if I look at those means, what were they? 2, 11, and 12, like that. If I look at those means, I know my type 1 error rate is probably going to be higher than the 0.05, so I'll just maybe adjust it if I'm interested in just pairwise comparisons. It's a rough adjustment. Nobody will really know exactly what your type 1 error rate is because we don't know what's going on in your mind, but it helps get a handle on it, okay? Number of means gets larger, it's not going to be very good. So Bonferroni can be used before or after. Now that we have the spirit of what's going on, what are these post hoc tests gonna do? So we have one post hoc salesperson and another post hoc salesperson come to visit us, and they're trying to sell us their post hoc test. What could be the only way that their post hoc test is really gonna be different? So the first person comes in and says, I've got a new post hoc test, and they describe the post hoc test. It's gonna be in the way it controls for the type 1 error. Okay? It's gonna be in the way it controls for the type 1 error rate. And different tests will control for it in different ways. Okay? I mean, if we put them on a spectrum, let's put these tests on a spectrum for the post hoc. Post hoc tests. What's the spectrum we can put them on? So we're gonna say this is low on the spectrum and this is high. Take two post hoc tests, which way are you gonna wanna compare them in terms of, as a researcher? Well, you can think of them as being conservative and liberal. Okay. Everything's politics, okay? So conservative and liberal. If I say I've got a post hoc test that's very, very conservative, very, very conservative. You can just say this is lower and higher, or you can just say conservative and L. Just defining the length of the dimension we're comparing these on. What it means to have a conservative test. And I say, I've got a post hoc test that I've used for my research, but it's very, very conservative. Yeah, let's think about it. Maybe over adjust, and maybe it doesn't over adjust, it's just pretty hard, right? If you find a statistically significant difference with a conservative test, really conservative one, what are you pretty certain there is going on? Yeah, it looks like there's probably a difference, right? It's like the hard test, right? It's like if you can find a difference with, we're gonna call it the Chaffee test, you probably, boy, there's probably a difference there. Probably, you got pretty good evidence there's a difference. Okay, so if we look at over here, more liberal test. More liberal test. What would be a characteristic of a more liberal test? Say, you know what, boy, I mean, what is that conservative test kind of? It's nice if you can reject the null hypothesis with the conservative test, but what's the problem? Yeah, you get no what? Power. Get no power, right? It's like, I understand you want to be sure if there's a difference there, but we're not rejecting anything. Right? We're not rejecting anything because it's just too hard of a test. It's just too hard. So then you start going the other way in the spectrum, and then you get to the extreme on this side. And what's that extreme? Yeah, that salesperson comes in and says, yeah, I heard you're having trouble with those really difficult post hoc tests, eh? My goodness, they're much too conservative, much too hard to pass, low power. Let me go completely to the opposite extreme. Here's a test for you. What are you doing here all the time?
Rejecting.
Yeah, rejecting all hypotheses, making lots of type 1 errors. Say, just use this, just reject everything in sight. Just reject everything in sight. So if it's too liberal, if it's too much on that extreme of the dimension, then you're rejecting left and right. And I mean, I'll ask the question, what's wrong with that? Why would you not prefer this test? Which one's gonna look better for you publishing something, especially if your audience doesn't know the difference between these tests? Which one are you going for? You're going for the liberal one. You say, found a difference, found a difference, found a difference. Look at me, found a difference. The only problem is that the person knows post hoc tests are gonna say, crappy test. crappy test. You're finding differences with a crappy test. How about differences somewhere over here? Then I'll believe you. Then I'll have more certainty in the result you've obtained. Does that make sense? Okay. So there's the idea of post hoc. Let's just go back to the idea of the contrast. The contrast idea, we're going to define a contrast as C sub I, and then we're going to make a comparison on this. So we're going to say contrast is going to be the value we want to compute. The value we want to compute. It's going to be a statistic, and we're going to say the contrast is equal to mu1, mu2, mu3, and we're going to have to, let's put in, let's just keep the 3 means. And we're gonna have to assign values to this. So maybe in line with our theory, we're gonna say the first mean, 1 times the first mean, plus minus 0.5, that's not very clear, minus 0.5 times the second mean, plus minus 0.5 times the third mean. Now, what comparison have we made for this particular contrast? What we've done is we've compared the second mean and the third mean to the first mean. That's one comparison that we're making for which we obtain a C value. Does this make sense? Why did I assign the weights the way I did? I assigned them so it produces the balance. Under the expectation of the null hypothesis, what would we expect C to equal? So under HO, what's our HO here? Under HO, C would equal 0. Why 0? Why 0? Because if, yeah, exactly. See, we've assigned these weights. We've assigned these weights in a very strategic way so that it represents the contrast we want to make. 1, now I had to go plus minus 0.5. You said, why don't you just go minus 0.5? Because technically speaking, we're producing what's called a linear combination, and it's an addition of numbers. It's an addition, but you can also add a negative to it. So it's 1 times the first mean plus negative 0.5 times the second mean plus negative 0.5 times the third mean. Under the null hypothesis, we see that if there's a perfect equality going on between this versus this, then it should come out to be 0. So we can say that the expectation is equal to 0. What are we looking for as a researcher? Do you want it to come out to 0? No. You're looking for something different under the alternative hypothesis. So under H1, the expectation is what? Is it equal to 0? No, unequal to 0. Right? Under the expectation of under the alternative hypothesis, the expectation is that would be unequal to 0. So let's say that our C value comes out to be, let's just use a number. Let's say it comes out to be C sub I is equal to 3. Let's say that that's what you get from your contrast. You plug in the real, now we don't have the population numbers, right? You're putting in sample data here. So this is a population comparison. But when you get your data, you don't have the population means. Otherwise, if you had the population means, you wouldn't be doing this, because you just say this means different than these two and it's over. So you actually get what? Mean 1, mean 2, and mean 3. So you're making the comparison, and let's say you get a C sub I value of 3. What's the next step? The C sub I value of 3 from this. Look, if it came out to be 0, case closed, even with sample data, because it's sample data, say it comes out to be 3. What do? C sub I comes out to be 3.
Ask what the probability is.
Yeah, that's what the probability is. That's exactly it. That's not even a joke, right? You asked what the probability is. Do you mean that as a joke? You did? Really?
No, I mean, yeah, it's just funny to me because it just repeats over and over.
I know, 3 hour classes. So C sub I is equal to 3, you ask what the probability is. This is kind of like if you obtained, what, like a T, like a Z, like an F, you're saying, hey, what's the probability of this happening under what? Under the null hypothesis. What's the probability, what's the prob of this under the null hypothesis? Well, if it would have happened at 0, you wouldn't be asking the question, you'd say, wow, that's right in line with the null. But you've got something different from 0, so here's the big test, right? Here's the thing, see if we're understanding this. You got your C sub I value comes out to 3, you ask the probability of it. Can you do the next step? We'll look at the formulas in a second. They're not that enlightening, actually. But when you look at that, you say, well, what's the probability of getting a 3 under the null hypothesis? What's the only way you're gonna determine that probability?
Distribution.
Compare it to a distribution. Does everyone see it? You're gonna have to compare this to some distribution under the null hypothesis. And it ends up being a T distribution. Compare it to a T, and it could be converted to F. You're gonna compare this to a distribution to determine that probability. Let's say that after you make the comparison to the distribution, this ends up being, probability is, say less than 0.05, again, it's arbitrary, but let's say 0.05, what do you conclude? You reject the null, and what do you conclude?
There's a difference.
Yeah, difference where, in the sample?
Population.
Population, right? You say, you know what? Based on this sample data, hey, I think my true comparison in the population is unequal to 0. In other words, what you found evidence for is what? Mean difference, these two versus this one, because that's how you set up your contrast. Make sense? Make sense? Kind of? Now, here's one other thing. You see these weights? What do you notice about these weights? These are called scalars.
Yeah,
And you get this
zero.
part of linear algebra. These weights are, they sum to?
0.
They sum to 0. They sum to 0, and it's very important that they sum to 0, and they reflect the comparison you want to make. So I'm not arbitrarily choosing those weights and going, 0.6, 0.4, whatever. I'm actually choosing them in a very interesting way so it reflects the comparison. But the truth is I could have also set this up as, well, how could I have maybe done it? What if I had done something else? Like, what if I had done this? Instead of 1, I just got this fascination with 10, and is that okay?
Sure.
Yeah, everyone see why it's okay, right? It's still reflecting the comparison. I'm just multiplying the weights. So it's not the actual absolute values of the weights, it's the comparison that matters, and it's very, very important that the sum, what are these weights gonna be called? Well, let's give them names. Let's call them C weights. Okay, let's call them C weights. The sum of C has to equal to what?
0.
0. If it's not equal to, I mean, let's just entertain the possibility it's not equal to 0. I'm gonna just produce weights that don't equal 0. What's the problem?
You're not gonna equal 0,
What is it? I'm gonna say, I'm gonna do a contrast, but my sum of my weights, I'm gonna say doesn't have to equal 0. I'm gonna say is equal to 2. What's the big problem with that? I mean, it seems quite arbitrary that it should have to equal 0. What if it's equal to 2? What's the problem with that? Yeah.
doesn't tell you.
Well, let's see. What if we said, well, I'm gonna make a comparison, I'm gonna try my best to do it, but the sum of the weights is gonna equal 0. Here's the issue. We don't have a null hypothesis representing this situation. Does it make sense? We have a null hypothesis representing this situation here. So our null hypothesis is centered at 0 of the idea of no difference. Therefore, we want the weight. It's almost like a convenience to just say get the weights to equal 0. Then we'll know what's true under the null. Does everyone see that? We'll know what's true under the null And then what are you looking for? Deviation from that ideal. Deviation from that ideal, and if you get it, if you get a little bit of deviation from the ideal of 0, you go, must be happening between 2 and 3 versus 1, because that's how I formulated the comparison. Makes sense? I could do another comparison. I can compare means 1 and 2 to 3. What would I have to do? Change my weights. One hypothesized comparison, I'll do another comparison, I'll do another comparison. So the question is, why don't I just do comparisons this way? And say there's one comparison, there's another one, there's another one, there's another one, just do lots of comparisons. Eventually something's gonna come out, it would seem. What's associated with each comparison I do? Yeah, type 1 error rate. You can get a type 1 error rate. So associated with this comparison is 0.05. Let's do another comparison. Let's do another comparison. Let's do another comparison. 0.05 starts to add up. Again, it's not quite 0.05 plus 0.05 plus 0.05. That's nearly so. It starts to inflate. So now we can appreciate why, if you're going to do contrasts, how many should you do? Theoretically, how many should you do? Maybe 1 or 2, depending on how many means you have, but not that many. These are planned comparisons. You're doing contrasts when you have a pretty good theoretical rationale of what you expect to see based on your theory. So I'm gonna pose this next question and say, which one would you rather have, right? Which one's gonna give you more power, contrast or these like post hoc things? Yeah, the contrast. So why don't you just like do a whole bunch of contrasts? Just do a whole bunch of contrasts. Do one, another one, another one, another one. If you do the same post hoc, what's the post hoc gonna do? Is it gonna make it easier or harder?
Harder.
It's gonna make it harder. So why not just do a whole bunch of contrasts? Do contrast versus 1 versus 2. You can even assign this a value of 0. Assign that 0 so you just get this comparison. Do another one, run them all as contrasts. Then present your results, maximum power, because you get 0.05 for each contrast, and then present that at the conference. What's the problem with that? What's the problem with what I just suggested? Just keep running a whole bunch of contrasts. Because I'm telling you, the contrasts have more power. This post hoc idea is not a nice idea for us. Like, as researchers, the post hoc are like, oh, what's the post hoc gonna do to me, right? So, run contrast, but what's the problem with that? What's the problem with that? What's the person at the contrast, not the contrast, we are in classes, where are we? Conference, yeah, at the conference. What's the person at the conference gonna say? Gonna say, you ran like 4 or 5 or 6 or 7 contrasts? Right? They're gonna say, you ran like 4 or 5 or 6 or 7 contrasts? And what are they gonna say? In other words, you actually almost pretty much exhausted all your contrasts, right? You had, let's say, 10 contrasts available, 10 possible contrasts available, and you ran them all. What's the critique?
You're supposed to reduce it all down, right?
Okay, what she says, you're supposed to reduce the type 1 error rate. What's your defense? You say, you know what, I had them all planned. I predicted all of these differences that we see.
How did you do that?
Well, this can be a tough sell, let's just put it that way. For you to kind of say, you know what, I predicted every one of these contrasts I predicted, therefore no correction on the error rate is necessary because they're all planned in advance before I looked at the data. People are gonna call foul on you and they're gonna say, no, no, no. And they're gonna tell you what? Nicely. What are you gonna say? Say, you shouldn't be doing contrasts. You should be doing what? Post hocs. You should be doing post hocs. So if you want to exhaust all of your contrasts, go ahead, but the journal reviewer are going to look at it and they're going to say, why are you doing 10 contrasts? This should be a post hoc. And if you say, but they were planned in advance, they're going to say, yeah, whatever, right? You just wanted to get more power to do your comparisons. This should be definitely a post hoc. Make sense? If you do 1 contrast, or maybe 2 out of, say, a possible 10, then what's the story? That's more believable, right? You say, okay, we can buy that you had a theoretical prediction. Maybe the adjustment on alpha is not necessary because you're only doing a couple planned comparisons. See, the thing is when you publish this stuff, nobody knows whether you looked at the data or not. Nobody knows. But as your number of comparisons increase, what starts to kind of, you start to say, well, either you looked at the data or you're just exhausting every possibility. That's like the weather person saying, you know, Cut Bank will get more snow than Montana, Montana will get more snow than Butte, Butte will get more snow than et cetera, and then the data come in, you say, see, I was right in a few situations. I'm gonna say, yeah, but you predicted everything in sight. So if I take this, and I say, well, this could go this way, this could go this way, this could go this way, down, it could do this, it could disappear, it could do that. I've exhausted the whole grid, and then when it happens, I go, see, I told you so, no one's gonna believe you. That's the idea. Okay. So, continue on with the chapter 4. We'll recap some of these topics next week. What we've been talking about, we get into post-hocs, contrast, again, skip the gray, get up to here. Null hypotheses, we talked about those. Talked about assumptions last week. Remember fixed versus random effects, we'll recap that stuff. Skip the nesting, you can read that over, but we're not gonna be like covering balance versus unbalanced, number of observations per cells. It's always gonna be balanced. Here's where we talk a little bit about that, for now it's gonna be balanced. Eta squared, and we went to omega squared, talked about that. Another form of doing omega squared is there, but that's the one we looked at. Pretty much all you need to know for omega. F-test and independent samples, T-test, if we have time, we might look at that. Probably won't have time for it. But there's a relationship between the F and the T. So if you lose your T-test software, you can always just do an F-test because the relation is T is equal to the square root of F. So the sampling distributions are related. And you may have kind of figured that intuitively too. It's like, why do we have to do a T-test when we got, ANOVA doesn't have to be on 3 or more means, it could just be on 2. There's a relationship between the two. So comparison of 2 means, do an ANOVA, or you can do the specialized T. Contrast and post-hocs, there's the idea. Population comparison is what we had up on the board. Right? Those are our C weights. Right? There's the comparison, our little C weights. Well, it's equal to the sum of the C weights times the means. So this is called the linear combination. And here's an example of the contrast. It's a little bit different than we did on the board, but it's mu1 plus mu2 versus mu3 and mu4. Population comparison, you can see that the weights sum to 0. There's the weight summing to 0 right there. Get your sample means, put it in there, and see how much it deviates. Right? See how much it deviates. The expectation of the contrast is equal to the contrast value. So that's good. It's an unbiased estimator, which makes it nice. And we look at the example. There's an example. What do we have there? Well, that's based on the data in the chapter. So we have 71 plus 72.5. There's the first group, plus, minus 1, plus, minus 1. Again, remember, we're using these plus here. That may seem confusing. Let's just go minus 1, minus 1. Because technically the linear combination is an addition of terms, even if you're adding negative terms. So that's just to make it completely general. What do you think of this? 27.17, different from 0. Who cares about the sign, really? Scientifically, you'll care about the sign as to which ones are bigger. But you look at the 29.17, what's the probability of obtaining a result like that? Well, what are we gonna need? What's the probability of obtaining a mean of 130 from a group that has a mean of 100, the population? What did you need? You need a distribution. And what's gonna be key to that distribution? What type of distribution do you need? Sampling distribution. Is everyone on board? Sampling distribution, you need the sampling distribution so that you get the expectation of the sampling distribution. The expectation is equal to 0 under the contrast value, but now, what do you care about? Standard error, right? What's the standard error of the contrast? What's the standard error of the contrast? In other words, you're seeing this is the same thing as a t-test. It's the same thing. It's just a more complicated comparison. If this was a t statistic, you would say what? Well, it's different from 0, so I've got some difference going on. What do you compare it to in the denominator? Standard error. Standard error of the mean, or the difference, or whatever you're analyzing. That's a contrast. Compare this value to the standard error. What would you expect to see under the null hypothesis? Well, a little bit of theory here, but look how it's going to work out. It's going to be a t statistic of your contrast value minus the contrast value. There's a hat missing somewhere in there. I'll have to get back to you on that. There should be a hat. It's not printing on the PDF for the hats. I apologize. the hat value minus under the null hypothesis over the standard error of the contrast, okay? Over the standard error of the contrast. This is identical to the idea of the ordinary t-test. Again, the comparison is a little bit more complicated. So there's an example in SPSS where we did a contrast of 1 and 1 versus -1, -1. You can see what's happened. Well, let's assume equal variances for a second. There's our contrast value of -29. What's that number? Standard error of the contrast. You want it to be big, you want it to be small as a scientist.
Small.
Yeah, you're cheering for small. Why? Because it gives you more what? Power. Everyone see it? It gives you more power to reject the null hypothesis. If this starts to go up, right, if your data are such that this starts to go up, then how excited are we about this? Less so. Because we say, you know what? Yeah, that contrast value is different from 0, but actually it's not that extreme because your data is a mess. But that 29 ends up being pretty extreme here. And we'll look at the p-value. It's not equal to 0, but SPSS and another software rounds it. So that could never be equal to 0 exactly, but it's pretty darn low. So what's your conclusion? The conclusion is, hey, in the population, I think mu1 and mu2 are different from mu3 and mu4, okay? We'll continue this stuff next week. I'll just show you a little bit where we're at. There's we get into post hoc. So a good idea would be read that, read sections of the book. We're in the ANOVA chapter for post hocs, and we'll need to discuss how this test works. This is a pretty old test. It's still used sometimes, but it clearly demonstrates the logic of how the post hoc test operates. Okay, so we'll go through that next week. Now we'll talk about the different post hocs, Tukey, Chaffee, and you'll get an assignment next week. I'm not getting it this week, but next week, where you'll have to do some power analyses and do analysis of errors, etc. Okay, that's where we're headed. I've also posted, next week we're definitely into the chapter 5 stuff, which we've started on the board. So we're gonna move fast through that. We're gonna move very fast through that because all the stuff is here. And there's chapter 5 on the factorial ANOVA. And that's also in Montgomery, okay, but those are nice summary notes. And hopefully my goal is by the end of next class, we'll have covered all the essentials of this, because we're pretty much there. In fact, factorial ANOVA, we're almost there in terms of the rest is the technical details that we look through. And then we're gonna be probably getting into the regression chapter pretty soon, okay? Okay, so have a nice day. Oh, you want your tests? Just in case you want that.
Oh, thank you.
Okay, so if we take a moment to talk about the tests. Oops. Look back at the syllabus. Just want to make sure what I'm saying is actually true. Okay, so there's your midterm right there. Now, your final exam, remember so that's 30%. Now your final exam is 50% plus, what did we say at the beginning? Could contain this 30, right? If you do better on the final exam than you did on the midterm, okay? So in other words, what's true about this midterm test? This could be completely disappear. It could completely disappear if your final exam is good. Your final exam could be worth 80% of your final grade. So let's say in theory that you got 0 on this. You still have a chance of getting an 8? Absolutely. You still have a chance of acing the course. Let's say that you got perfect on this. What's true? You still have a chance of doing very badly in the course, okay? So that's what every year, I said this at the beginning of the course, that the midterm, it's like a sports team doing good in the regular season. It doesn't really matter, right? It matters what you do in the playoffs, and the playoffs are in December. Okay, one last thing on the night, and then I will shut up. Just give us the darn midterms already. I've posted a key, I may as well make this stuff public. Okay, there's the key. Just explain a little bit again on how this is graded. There are a few items, a couple actually, that, you know, when I've graded these, I gave Brandon the week off, so one thing you'll notice at the end of some of your papers, there's like 2 or 3 or 4 scores and some of them are scratched out. It's the way I grade it when I'm trying to figure out where the distribution, not the distribution, but what types of questions people are having trouble with. Like the last question, remember that last question, all of that? That question I originally was thinking, well, when I looked at it, I said, maybe I can give 3 points for that and make the whole test out of 32. But that was a tough question for everyone to get right. So we reduced it down to 1 point. And the way that worked is basically if you're on the plus side, you got the point. So in other words, if you're circling all the bad answers, you're just gonna get 0 out of 1. If you circled plus a good answer, and then a whole bunch of bad ones, you got 0. If you circled 2 good ones, 2 bad ones, you got the point. If you circled good one, good one, good one, bad one, you got the point, like that. There's no test where it was like right down the middle, and if it was, you got favored in terms of getting the point. Okay, so just to explain how that one was graded. The other issue is, there was one of these for this one here, number 3. The answer is it's a discrete random variable. The random variable is not perfectly normally distributed because a perfect normal distribution is a perfect curve. However, quite a few of you said, well, it looks like a normal distribution, so we allowed that as well, which means that these stars say those were acceptable answers too for them. Okay, but there's your best answer. The other issue too is, remember how these are graded in terms of part points. So you look at something like this and you go, A and C is the correct one, but if you did this one, you get 0.5, and if you did this one, you get 0.5. So keep that in mind. Okay. I think that's it. So the score at the end of your test is highlighted in yellow, and that's the score that we've recorded. To these, because there were a couple questions that were fairly low on the class average, take whatever score you have here and add 2 raw points to it. So whatever score, add 2 raw points, and that's going to be your midterm score. And that'll be it for today. Jennifer Rato. One more thing about these two is, we think about what's going to be on the final exam. Make sure that if any of this is unclear, that you get clarification on it, because the same principles will come up. Todd Marchand. Alisa Germscheid. Germscheid? How do you say the last name?
Germscheid.
Jenna. Yep. Jennifer Villa. Kelly Davis. Megan Miller. Delaney. Amy Villalon. That's right. Oh. Jane Reynolds. Erica. Ian Dunn. Ashley Dash.